Okay, guys, so in this short video, we are going to talk about the simple harmonic motion, Hooke's law, and the simple harmonic oscillator. Okay, so how can you say something is doing simple harmonic motion? Well, the specific type of motion in which that you have a force which is proportional, right? You have a force, oops, you have a force which is proportional to the displacement. So you have a force which is proportional to the displacement, which is x. Okay, in that kind of motion, we can call that is a simple harmonic motion, right? So if you remove the proportionality sign in case of a spring, we can have your force F, which is exactly equals to your negative kx, and that is your Hooke's law. So when you apply the force and the object moves, the spring wants to go back to its original position. And that's why the negative sign comes from. And that force, we will call it as a restoring force, F restoring force or F spring, which is exactly equals to negative times kx. K is your spring constant, has a unit of Newton per meter. So unit for a spring constant would be unit Newton per meter. Okay. And that's how we can derive the simple harmonic motion of any spring block system. Okay. So in this first diagram, what I have is a block attached with the spring. Of course, as you can see, there's negative A, 0, and A. A stands for amplitude, which is the maximum displacement. This is the maximum stretch or compress one can go. So if the situation one, you can look here, you will have your force that is going to be your maximum amount of force you have when you are compressing it. And when you are compressing it maximum, your x, which is a displacement, would take place as an amplitude because that's the maximum displacement you have, right? And in that case, you will also have at that point, at exactly this point, you will have a acceleration as your maximum acceleration. Also, at that point, your instantaneous velocity is 0 because the object is going to come to stop at the amplitude, and your position, which or the displacement from the equilibrium, would consider as a negative A because you are at a negative A. So this is the situation when you are compressed at the maximum displacement, which is at a negative amplitude, negative side of the amplitude, right? So the spring block system will oscillate between the positive amplitude and negative amplitude or anywhere in between, right? But the maximum you can go is just A or minus A. Okay, think about the second situation where you are is, so you compressed first and then you let go. This oscillator will gonna come to a 0 meter mark. And when it coming to a 0 meter mark, your force is going to be 0. Your acceleration at that point is going to be 0 as well. Your displacement, because you are coming to an original position, your original length, so your x is becoming 0 as well. And your velocity is actually going to be a maximum velocity at that equilibrium point, which we call it as a v max. Okay, keep going. After achieving equilibrium position, your the spring block system will keep stretching itself to the positive amplitude. Again, you are at the positive amplitude. That means the spring wants to go back to its original position, right? And hence we have the maximum force. We consider that as negative, right? So here's the restoring force. If I draw it with the different color marker in the first diagram, the restoring force is pointing that way because the spring wants to come back to its original position. This force has to experiencing in that direction. Here the force is experiencing in this direction because it wants to go back to its original position. True? So that's why we can consider that F is F maximum. Go back to the red marker here. You have that F max is a negative of Ka because it wants to go in the original position. Your acceleration is going to be a negative maximum acceleration. Your velocity is of course 0 because momentarily you come here at the maximum displacement, your velocity is 0. And your x, which is going to be A. Your x, which is going. So now we have a block system which is going back again in the opposite direction. So from that point, it's coming to a zero position back again. We're gonna have the same thing. V is you going to be your V maximum negative. Your acceleration is going to be zero at that point because there's no change in velocity. Your force is zero because nothing is forcing at that point, at that location. Your displacement is zero and such that. Right? So you can see the block spring system is going back and forth between the amplitude A and minus A, and how their force and acceleration is changing. Now with this, one can also do, can I copy this? Let's see. Nope. I think there was a button for copy. Basically, you can do the same thing and derive the energy for all the situations, right? What is the energy in all the situations? Actually, we can write here, right? Look at the first case right here. If you have, let me erase this. Oops. Okay. So let's look at the first case. You have the object at x equals to negative a. What kind of energy this oscillator has? Now, I use the word oscillator. Anything which is oscillating with the simple harmonic motion, we call it as a simple harmonic oscillator, right? We call it as a simple harmonic, simple harmonic oscillator. So any object you take which is doing a simple harmonic motion, we can call it as a simple harmonic oscillator. It has a two type of energy, as you know. It has a spring's potential energy and it has a kinetic energy, right? Spring potential energy, you can derive it as a 1/2 kx squared, right? Spring's potential energy or elastic energy can be defined as 1/2 kx squared, and we'll define it one more time on the other side in a minute. And it has a kinetic energy as 1/2 mv squared for sure. Right? So at each different location, for example, here or here or here or here or anywhere in between, there is a more than one energy in some cases. In some cases, there is only one energy, but the energy conservation is still a valid thing in a spring block system as well. If we write that in terms of a total energy, we can say your E total for a spring block system is definitely a kinetic energy plus the elastic potential energy, and that is considering as a 1/2 mv square plus 1/2 of kx square. Of course, if you want E total, what is the maximum mechanical energy of the spring block system can have is E total, and that can be exactly 1/2 ka square. Right? So your E total can be E total equals to 1/2 ka square, kinetic energy 1/2 mv square, and potential energy is 1/2 kx square. Now, anywhere in between, going from maximum amplitude to the minimum amplitude, going from A to negative A, you can have this type of energy. Energy is going to always transfer from one form to another, kinetic to potential, potential to kinetic, and vice versa. Okay? So, if we talk about specifically for this time, that in my situation number 1 right here, what is the energy the object has? What is the energy of the spring block system has right now? Of course, you are at a negative A. That means you don't have any spring potential energy, or you could say you have only spring potential energy, and that your R at x equals to A, that means your maximum spring potential energy is 1/2 ka square, right? So the energy you have right here is your 1/2 ka square. That's it. You don't have any kinetic energy. Got it. Now, let's say you are at a position number 2 at the equilibrium position. So you swinging back and forth, going from A to B, going from maximum amplitude positive A to the minimum amplitude negative A. Here you're going from negative A to the 0 to A. Now when you are at A, you don't have any elastic potential energy. You only have, yes, only kinetic energy, which is V max square. Do you see that? All right, you keep on going. You keep on going. In situation number 3 now, you are going from 0 to A, right? You're going from 0 to A. And now you again bring up your maximum potential energy. And in that case, it will become, let me change the eraser size so that I can erase this F. Oh, okay. I can erase this F. And I'll make this here energy because I want to write the energy here, right? So the energy right here is coming out as a 1/2 Ka square. That is the only energy you have. There is no kinetic energy. Now, fourth position. Let's say this is the same as number 2. So I'm going to change that to, I'm going to change this one to a different location. So let's say block spring system is not at A, is not at 0. It's somewhere in between. If something is somewhere in between, where can it be? Okay, I want red mark. Okay. Okay, so let's say it is right here. So it's not at X, it's not at A, it's not at 0, but it is at some distance X. So at this location, what energy you have? Well, at this location, you definitely has both energy. At this location, you have both energy, 1/2 mv square, and you have 1/2 kx square, for sure. True? So all in total, we are saying that your energy graph with the position or with the amplitude, let's say going from negative A to positive A, your elastic potential energy is changing and your kinetic energy is changing depending on where you are, right? So I'm going to draw this as energy versus displacement graph. The total energy may be somewhere right here, which is going to keep it constant, right? The total energy keep constant right here. I will make sure that this is the E total. The parabolic path we are getting right here, that is the kinetic energy, because the kinetic energy is maximum at a 0 location, as you can see here from the graph. And now the one which we need to draw, we're going to draw it with the maybe a blue marker, which is the potential energy, yeah, elastic potential energy for the spring. So this is the elastic potential energy for the spring, and we will name it as UE. True? So flashback or reverse back or review what we have learned so far. Okay, we started from simple harmonic motion, F equals to negative kx, using Hooke's law. We derived what is F, acceleration, velocity, displacement is going to be at any particular position in block spring system. Then we went ahead and derived the energies. What are the energies you have at any given location and how you can find out. The last thing I want to share is how did I get 1/2 kx square, right? Elastic potential energy. And that is what I want to show you right now. So we know one relationship, which is F equals to negative kx. And we also know that the work done from our energy unit, work done is going from x equals to x. If I want to move the spring block system from one position to another position, I have to apply the force. And that force times the distance is considered as a work done. But I know what is the work going to be, because I know the spring would always want the force going to be negative kx. So your spring force is a negative kx. I can integrate using a negative kx dx. And I will go from equilibrium position 0 to some distance x. Okay, instead of going from x0 to x. This leads me to the integration of negative 1/2 kx squared. I will take it out. I'll go from 0 to x. 0, if I put it, nothing is going to come out. That means my work is a negative kx squared on the spring. Look, I did work on the spring, hence the work is negative. So you can say that the spring gained the potential energy as a UE, which is a negative of work, which is exactly equals to 1/2 kx squared. This is how I got my elastic potential energy for the spring. All right, that's it for now. Thank you.